What's up, everybody? Hope you all are doing well. Today, we are going to be going over 10 two-dimensional kinematics review problems. So I'll link the PDF down below if you want to take a look in advance, but otherwise, let's just go ahead and jump right in. So in problem number 1, we have a player kicking a football. Okay, it's going to go in the air, and there's a few parameters we know. For example, we know the distance here, 82 meters. We know the time in the air is 4.1 seconds. All right, and what we're looking for ultimately is like how fast is the player kicking the ball. So let's go ahead and write down what we know. So remember, we are going to isolate our x direction and our y direction. So we'll throw down our variables. So v initial, v final, acceleration, displacement, and time. And we'll just kind of write these down for each of our 2 dimensions. So the initial velocity is unknown for both. Final velocity is unknown for both as well. The acceleration in the x direction, this is going to be 0. Once it's in the air, there's going to be no air resistance, nothing slowing it down horizontally. Now vertically, we are going to have a negative 9.8 because gravity is the only object acting on it, slows it down on the way up, speeds it up on the way back down. The displacement in the horizontal direction, we can see that's going to be 82 meters. In the vertical direction, since we end up where we started, we're going to say that that is 0. And then the time for both is going to be 4.1 seconds. So remember, the key number of variables you want is 3. And since we have 3 for each of these, then we know we can find the v initial for each of them. So let's go ahead and do that in the x direction. We're going to use this equation, delta d equals VOT plus 1/2 AT squared. All right, and since acceleration is 0, that really simplifies the problem. So this is going to be 82 equals the initial times 4.1. Solve for the initial, and you get 82 over 4.1, which gives us 20 meters per second. Now remember, that's not the total velocity. That's not what we're solving for. That's only the horizontal velocity. We're also going to need to solve for the vertical velocity. So we'll go ahead and set this up the same. And I'm going to use the same equation. So VOT plus 1/2 AT squared. Okay, so our displacement is 0 this time because we end up at the same place that we started at. The initial we're solving for, the time here is 4.1 seconds plus 1/2, negative 9.8, and then we're going to go 4.1 squared. So go ahead and do the algebra on this. When I do it, I get a v initial of 20 also. So notice that means we have 20 in the horizontal direction, we have 20 meters per second in the vertical direction. So we're going to solve for the v total here, and we're just going to use the Pythagorean theorem. So that means 20 squared plus 20 squared should equal like the v total squared. Right, so when you do that, I get 28. And then we're also going to solve for the angle. So this angle, now you can see this is an isosceles triangle, so the angle is obviously going to be 45 degrees. But if it wasn't, if you didn't know what it was, then you would just use kind of your tangent function, inverse tangent of the opposite. So that would be like the Vy here over the Vx, and solve for it that way. All right, let's move on to the last part of the problem, letter C. So for letter C, we're looking for the maximum height. So how high did it reach? So for this one, notice all we really care about is the vertical dimension. So we care about the y dimension here. So for example, we already know the v initial in the y direction. We solved that in the last case. That's 20. Okay, and then the key thing here is as it's rising, it's slowing down, and then it temporarily stops. Vy, we'll call it at the final here. It temporarily stops at the peak. Okay, now that doesn't mean it stops completely. It just stops rising, and so the vertical velocity is going to be 0. The acceleration is still gravity, and then we are solving for a displacement here. Okay, so we'll be using this equation, vf squared equals vo squared plus 2ad. Vf is 0, v initial is 20. Remember, that's just the vertical velocity, 20. And then we'll go negative 9.8 times d. Okay, go ahead and solve for this. So 20 squared gets negative technically divided by 2 divided by negative 9.8. And I get 20.4 meters. Okay. All right, let's move on to question 2. So question 2, similar question. We have someone kicking a ball. It's going to fly through the air, right? Land on the ground. And the parameters they give us are similar but different. So as usual, let's set up what we know. And again, we're going to do our 2 dimensions, so x and y. So in the horizontal direction, we do not know the v initial. So this one, as opposed to the last problem, this one, we know this velocity here is 12. So we do not know the initial x velocity. We do not know the final x velocity. The acceleration is going to be 0. It's pretty much always 0 for these problems unless they say that there's air resistance. Our displacement is also unknown. Our time is going to be 2 seconds. Now in the vertical direction, v initial is also unknown. V final is also unknown. Acceleration, again, this is going to be a projectile motion problem. So our acceleration is just going to be the acceleration of gravity. And then our displacement, again, if we land at the same height, we're going to say that this is 0 meters. And then the time is 2 seconds. All right, so notice we have 3 things on the y side, so we can find our initial velocity and our final velocity, but in this case, what we're really looking for is that initial velocity. Notice if we can find that initial velocity here, then we can solve our triangle. We can find the angle, we can find even the horizontal velocity as well. So let's go ahead and do that. All right, so we'll use this equation, d equals VOT plus 1/2 AT squared. Displacement is 0. The initial is unknown. Time was 2 plus 1/2. Acceleration is negative 9.8, and the time is 2 squared. So when you solve this out, this is going to be 19.8 divided by 2 equals the initial, and you get 9.8 meters per second. So that means the initial y velocity is 9.8 meters per second. Now remember, we're looking for the angle here. So if we know the initial velocity in the y direction is 9.8, we can just solve the triangle. So for example, I'd use the sine function to do that. So say the sine of theta equals opposite, which is 9.8, over adjacent, which is 12. Okay, inverse sine that. So sine inverse equals over this mess right there, that equals theta. So when you do that, I get an angle of 54.8 degrees. So for part B, we're looking for the horizontal distance that we travel here. So notice here for the velocity in the x direction, we can finish solving our triangle. So for example, we use Pythagorean theorem, so 12 squared should equal the Vx squared plus 9.8 squared. And we can just go ahead and solve for that. So 12 squared minus 9.8 squared should equal Vx squared. And then we'll solve for Vx. Okay, don't forget to square root when you do this. I get a Vx of 6.9 meters per second. So notice that essentially gives me the third known value in the horizontal direction. And from there, we can go ahead and solve for the displacement. So we'll use this one, d equals VOT plus 1/2 AT squared. And remember, the nice thing in the x direction is this goes to 0 because of that 0 acceleration. So delta D is going to be 6.9 times 2, which is, what's that, 13.8 meters. So the last part of the question is asking to sketch a couple graphs. So let me go ahead and clean this up here. So we're going to sketch two graphs, Vx versus Vt. When I say sketch, you're not gonna like plot a bunch of points. You're just gonna make a rough sketch of this. So this one, remember the horizontal velocity. So we'll call this Vx. The horizontal velocity is constant the whole time. So this is just going to be a nice straight line. If we want to label the graph, our horizontal velocity, remember, was 6.9 meters per second. And that's just going to stay nice and constant here. Now on the y side, this one, remember, on our way up, it's going to be positive. On the way down, it's going to be negative. So at the top, remember, we started at 9.8 meters per second. Now, since it's a nice symmetrical journey, that means we're going to end at negative 9.8, right? So on the way up, it's 9.8 going up. On the way down, it's going to be 9.8 coming down. All right, and then we're just going to connect it. So this is a nice slope that looks like this, okay? In fact, we know the total time they told us was 2 seconds. So we could label this as well. This would be 1 second, halfway when we reach the peak. Notice at the peak, our velocity would be 0. So that should make sense. And the slope, I didn't ask you for the slope, but the slope is the acceleration of gravity, right? So the slope is negative 9.8 meters per second squared. Remember, the slope of the v versus time graph is our acceleration. This is another angled projectile motion problem. This time, though, the object, instead of landing at the same height, it's going to land below its starting point. We're going to approach it pretty much the same way. So whenever you have an angled problem, my recommendation is just to kind of break down the velocities right off the bat. So for example, this is 20 meters per second at 52 degrees. And so we're just going to find the horizontal component of velocity, which would be 20 cosine 52. And I calculate 12.3 meters per second for that. And then we'll calculate the vertical velocity, which would be 20 sine of 52. And for that one, I get 15.7 meters per second. So when we set up our starting values, I'm just going to go ahead and plug that in here. So this would be 12.3 and 15.7 for those two starting values. All right, and then we'll go ahead and fill in the rest. Two easy ones are the acceleration on these projectile motion problems, 0 in the x direction, negative 9.8 in the y direction. And then the one additional thing we know is that we're ending up below our starting point. So whenever we end up below our starting point, we're going to say that our displacement is negative 30. So we're going to say we're 30 meters below where we started. So we're ultimately looking for our horizontal displacement, but we don't have enough information. So we look on the y side, we have 3 things, 1, 2, 3. We should be able to figure out our time here. So let's go ahead and do that. I'll use this equation as usual. This is the most common one that you'll see on these types of problems. Would always go to this one first if you're unsure. So this is going to be negative 30 equals the initial, which is 15.7 times time, plus 1/2 negative 9.8 t squared. So notice here we have a t squared and a t. There's no easy way to solve this. Actually, the easy way, I guess, is to use the quadratic equation. So that's what we're going to be using in this problem. So first, let's rearrange so that we're in the proper format. So if we add 30, we're going to get 0 equals negative 4.9 t squared plus 15.7 t plus 30 meters. And then we'll go ahead and plug that into our quadratic equation. I'll leave it up to you to do that. It's just a matter, plugging it in, doing some algebra and solving it. So I get a time of 4.55, or remember there's always two solutions, negative 1.35 seconds. Now this is for time, right? So the obvious answer is going to be 4.55. We're not going to have a negative time. In fact, what negative time means is way back here at the starting point. If you can go backwards in time and through the cliff, you could find the starting point to be on the ground way back there. So for our sake, the answer is going to be 4.55 seconds for time, that is. And then we're going to go ahead and solve for our displacement. So this time we'll use our x values. Remember the time now, that's the same, 4.55 seconds. That's the same on both x and y. So I'll go ahead and use the same equation, delta d, this time though in the x direction. So we'll go VOT plus 1/2 AT squared. Remember our acceleration is 0 in the horizontal direction. So it's going to be 12.3 times that time, 4.55. And that gets me a displacement of 56 meters. So let's look at letter B here. So letter B is asking how high above the ground is the maximum height. So we're going to, again, just set up what we know, right? Now in this case, since we're really looking at the peak value here, the key thing we know about the peak is that the y velocity is 0 at the peak. So if we just set up our y values, we should be able to solve for it. So for example, the v initial from the previous problem, we got 15.7 in the vertical direction. And then the v final, or the v at the peak, however you want to look at it, that's going to be 0. Now again, that's the y direction. Remember, it's still moving horizontally, obviously. That's how it ends up to the right. But vertically, it stops moving. And then the acceleration is negative 9.8. So what we're going to do when we solve this, we're going to solve for our displacement. Now, in fact, this is really only going to tell us how high we are from our starting point. So this is going to give us this value right here. But then if you remember, this was 30 meters. So once we find that, we can find out how high it was above the ground by adding 30. So we will use, let's use this, VF squared equals VO squared plus 2AD. So V final is 15.7, that's at the peak. Oops, that's wrong, that's not at the peak, is it? That's the initial. So V final is 0 at the peak. The initial is our 15.7 plus 2, negative 9.8 times D. Right, do some algebra. We're going to get 15.7 squared. We're going to divide by 2. We're going to divide by 9.8. Actually, I guess these are both negatives, right? Negative, negative gives us a positive. And then I get 12.7 meters. Now remember, that's 12.7 from our starting point. So we're going to add 30 meters to that to give us a total height of 42.7 meters above the ground. So this problem, we have a ball rolling off a cliff. And one of the key terms here is the fact that it says it's a horizontal velocity. So when it says the horizontal velocity, that actually simplifies the problem. So our v initial in the x direction is 1.27, but our v initial in the y direction is 0, because all the velocity initially is going to be horizontal. So that simplifies the problem a lot. Let's wrap these up. So acceleration is going to be 0 in the x direction. Acceleration in the y direction is our usual, negative 9.8, gravity. All right, and then this time they tell us the horizontal displacement. So our dx is going to be 0.75. And what we don't know is our dy, our height. So let's find our time. So we'll use d equals VOT plus 1/2 AT squared. So d is 0.75 equals 1.27 times time plus, again, this goes to 0. There's no horizontal acceleration. So when you solve for time, what do I get for time? 0.59? Yeah, 0.59 seconds. So now we use that known value for time. We'll use our y variables here to go ahead and solve for our displacement. So we use the same equation. So this time the d is the initial velocity is 0 in the y direction. So that component, that term is going to go to 0. Negative 9.8 times 0.59 squared. Solve for d. So notice when you solve for d, you're going to get a negative number, 1.7. And that just means because the way we're solving this problem, we're finding where it is, where it ends, and it's 1.7 below the starting point, right? Now, when we talk about height, we typically talk about how high above you are. So you would just say, oh, the height is 1.7 meters above the water. So lastly, we're going to be looking for the velocity right before it hits the water. So we're essentially looking for this velocity here. So notice, since the x acceleration is 0, we already know the horizontal velocity. That's going to stay the same. What we do want to do is find the vertical velocity. So we have plenty of information here. We know all of this. We also know the time, right? So you can use an equation to find that. I think I'll use this, VF equals VO plus AT. So we're looking for the velocity right before it hits the water. So A is negative 9.8, and T we found to be 59. So I get a V final of 5.8 or about 5.78 meters per second. So again, that would be this part of our triangle, 5.78 meters per second. So the actual question is asking for the hypotenuse here. So we'll use our Pythagorean theorem. So we'll go 1.27 squared plus 5.78 squared equals, just call this V final squared. And V final we get to be about 5.9. We also want to get the angle. So you could use any sine, cosine, or tangent. I'll use tangent. So we get tangent of theta equals the opposite, which is 5.78 divided by 1.27. Okay, do theta tan inverse, and we get about 77.6 degrees. How would we state this angle? Well, you could simply say it's below the horizontal. Based on my picture, you could also, if you want to use your like north, south, east, west, you could use that as well. I think that's how when I wrote the key, that's how I wrote it. So you could write it also as 77.6 degrees south of east. Right, let's look at this problem number 5. Once again, this time we're going to hit a ball 60 meters per second. So the first thing we're going to do is go ahead and break down our initial velocity. So this would be 60 cosine 35. I get 49.1 meters per second. This one would be 60 sine 35. I get 34.4. So let's put those in for our starting values. In the x direction, 49.1. In the y direction, we have 34.4. Then let's just fill in the rest. So the acceleration in the x direction will be 0. In the y direction, we'll go negative 9.8. In this problem, we do land on the ground. So once again, that means our displacement in the y direction would be 0. And as usual, we're just going to try to find the time, and that's going to give us values for both the x and the y direction. So we have 3 things in y, so let's go ahead and find the time for that side. So we'll go delta d equals VOT 1/2 AT squared. Let's just use the y values for this. So 0 equals 34.4 times t plus 1/2 negative 9.8 t squared. We'll factor out a t here, so we have 34.4 plus, let's go ahead and do the math, 4.9 times t. So t is either going to be 0 or this guy is going to be 0. So obviously the t equals 0 is not the one we're looking for. We're looking for the other one. So 34.4 plus negative 4.9 t equals 0. We'll go ahead and solve for the time here. I get a time of about 7 seconds, 7.02 seconds. So we're looking for the range. So that means we're looking for our delta D horizontal. So since we know the time, we can now find the range. So we'll go ahead and use this. Again, we're using it for our x side. Again, remember the acceleration is going to be 0. So that simplifies that. So we got dx equals v initial 49.1 times the time 7.02. So that's going to get me a range of about 345 meters. So let's go ahead and solve for our max height. So again, we know a lot of the same things. In the y direction, we know the initial is still 34. We know the acceleration is still this. The displacement is not 0 now, right? That's what we're actually looking for. What is true, though, is that the v final at the peak is going to be 0. So again, at this top, we're no longer rising or falling, so our y velocity is going to be 0. So let's go ahead and then solve for the displacement to the peak. So vf squared equals vo squared plus 2ad. 0 equals 34.4 squared plus 2 times negative 9.8 times delta d. Do the algebra, and you should get a displacement of 60.4 meters. All right, so the last part of the problem, we're looking for the final velocity after 5 seconds. So let's go ahead and pull all this up. Final velocity after 5 seconds, right? So what that means is, if you imagine, remember this took 7 seconds to make the whole journey. That means halfway was about 3.5. So 5 seconds is somewhere over here. So we're on our way down here. And remember, the horizontal velocity stays the same. So this was 49.1. So essentially what we need to do is find the final velocity in the y direction at 5 seconds. And from there, we can go ahead and then do our Pythagorean theorem to find the actual final velocity. So our initial velocity stays the same, our acceleration stays the same, and then our time now is going to be 5 seconds. So let's use this equation, Vf equals Vo plus At. V final equals 34.4 plus negative 9.8 times 5 seconds, right? So when we solve for V final, you're actually going to get a negative value. So that is negative 14.6. And that should make sense, right? Because we are on our way down. We're on the second half of the journey here, and we're on our way down. That's what that negative means. So we're just going to finalize this by solving for our triangle. So this we found was 49.1. This we just found is 14.6. We're now going to find our hypotenuse. So we use Pythagorean theorem, 49.1 squared plus 14.6 squared equals our V final squared. Go ahead and do the algebra on that. And I get, what do I get? 51.2. And then lastly, we're going to get the angle so that we know the direction. So we use the inverse tangent of that. So theta equals inverse tangent of opposite, which is 14.6 divided by adjacent, 49.1. And that gets me about 16.6 degrees. And again, the way we would say this angle, if we use our north, south, east, west directions, south, east, west, we would say we are south of east, right? 16.6 degrees south of east. You could also say below the horizontal, that works as well. Either way is going to be good. All right, let's move on. All right, this problem, we're throwing a lead weight off of a bridge. We're going to see how far that weight travels. One of the key words here is the fact that it says it's a horizontal velocity. So that means the horizontal velocity, the x velocity is 22, but the y velocity to start with is 0. So initially it's only moving horizontal. All right, let's finish filling this out. So our acceleration in the x direction is going to be 0. Our acceleration in the y direction is negative 9.8. And then the other thing that they would give us is the height of the bridge. So that's 176.4. So it's going to be our vertical displacement. Now again, since it's dropping, so we're technically, when we hit the water, we're 176 below our starting point. We're just going to make that negative. So we know 3 things on the y side. That means we're going to be able to find the time here. So let's use d equals VOT plus 1/2 AT squared. So our d is negative 176.4. Our v initial is 0 in the y direction. And then we'll go negative 9.8 times t squared. Okay, go ahead and solve for t. I get about 6 seconds. Actually exactly 6 seconds. So that would be our time in both directions. And then we will just finish this up and find the horizontal displacement. So we'll go VOT. By now you know that the 1/2 AT squared just goes to 0. So that's going to get us, the initial is 22 times 6. 132 meters. So we have a different type of problem here. This is a vector addition type problem. So let's draw this out. We have a woman's going to be walking south 250 meters. And then she's going to be walking northeast, specifically 30 degrees north of east. So let's draw this out. If you can, try to draw this to scale. It doesn't have to be, but it kind of helps you visualize it a little bit better. So what we're ultimately looking for is, where is she from where she started? So if she started right here, we're looking for this vector here. So how far away is she from where she started? So what you're going to do is you're going to basically change all our vectors into horizontal and vertical components. So for example, this green vector, this is already a vertical component, which is good. The blue vector, on the other hand, we're going to fix this into a horizontal displacement and a vertical displacement. So for example, this side of our triangle would be 150 cosine of 30, which is approximately 130 meters. And then this side of our triangle is going to be 150 sine of 30, which is going to be, well, exactly 75 meters. All right, so we're looking for, again, we're looking for this red vector here. Now notice, watch what happens when I draw this in. It should kind of pop out what happens. So we're looking for this horizontal and this vertical for the red vector. And then we can use Pythagorean theorem to find the actual displacement. So hopefully you notice that this side up here is 130 meters, right? That's going to be the same as this length. And then this red vector, this vertical vector here, that's going to be 250 minus 75. So 250 minus 75. So that gets us 175 meters. Now we can go ahead and use the Pythagorean theorem to find this displacement over here. So we're going to go 130 squared plus 175 squared equals, let's just call it d total squared. Right, do the algebra, and I get a d total of about 218 meters. So that's that distance from the beginning to the end where she ended up. Now remember, for vectors, we also need the direction. So we're going to do that by finding the angle. So we'll use our tangent function here. So theta equals inverse tangent of the opposite, which is 175, over the adjacent, which is 130. Solve for the angle. I get about 53 degrees, 53.4 degrees. Now how we say this angle, we're definitely going to use our north, south, east, west. So this is north, south, east, west. So notice we are kind of in that southeast direction. Specifically, we are 53 degrees to the south of our east. So we're going to say this is 53 degrees south of east. All right, this problem, we got a puma. I'm just going to draw it as a circle if you don't mind. We have a puma, it's going to jump up. And they're going to jump at a 45-degree angle. And they tell us the max height that we reach this time. What we're looking for is this V initial. Okay, so let's do our usual. Now for this one, honestly, we only need the vertical values because all we care about is what's happening at the peak here, right? So for example, our velocity vertical is 0 at the peak. The height, so delta dy, is going to be 3.66 at the peak. And then our acceleration is the usual negative 9.8. Now from here, we can go ahead and find the V initial in the y direction. So we will go V final equals v initial plus at. No, we won't. We don't know the time, do we? Let's try this. Vf squared equals vo squared plus 2ad. There we go. Sometimes you try certain equations, they don't work. You find one that does. So this is going to be 0 equals v initial squared plus 2 times negative 9.8, and then our height was 3.66. So that gets me a v initial in the y direction 8.5, let's go 8.47 meters per second. Now that's not the answer, that's just the vertical velocity, right? So if we look at our triangle here, this is 45 degrees. We just found this side. So we found 8.47 going up. So this time we're going to find our hypotenuse over here. So I will use the sine. So we'll go sine of 45 equals opposite 8.47 over that hypotenuse, which we'll just call v initial. So v initial should equal 8.47 divided by the sine of 45. And that gets me a v initial of approximately 12 meters per second. There we go. So here's a fun problem. We have a soccer player. They're going to try to score a goal. They're going to shoot the ball. And we're trying to find out, do they score or not? So they kick the ball with the speed of 14 meters per second at an angle of 33 degrees. The goal is 5 meters away. And basically what we're trying to do is we're trying to see, so the goal itself has a height of 2.44 meters. So what we're looking for the displacement of the ball when it reaches the goal. And if it's greater than 2.44, we know that we missed. And if it's less than 2.44, then we scored. So that's what we're looking for. So let's go ahead and set up our known values. So v initial, so let's go ahead and solve this triangle here. So we're 14 at 33. So we're gonna go on this side, 14 cosine of 33. On this side, we're gonna go 14 sine of 33. Let's go ahead and calculate those. So 14 cos gets me 11.7. And 14 sine gets me 7.6. So let's go ahead and fill that in for our x side. The initial is 11.7. And on our y side, the initial is 7.6. Right, our acceleration in the x direction, as per usual, is 0. And the y direction is 9.8. Okay, the other thing we know is how far away the goal is. So that's a horizontal distance of 5 meters. Now, one thing to caution you is that we do not know dy. That's actually what we're solving for, and then we're just going to see is it greater or less than the height of the crossbar. So at this point, you probably know, all right, let's find the time. So we know 3 things in the x direction, so we should be able to find the time from there. So let's go ahead and use good old usual d equals VOT plus 1/2 AT squared. So our d was 5 meters. The initial is 11.7 times time plus 0, no acceleration in the x direction. So that gets me a time of 0.427 seconds. All right, and so that's also the time on the y side. That gives us our third known value. So lastly, we're going to do is solve for the displacement in the y direction. So that's going to be VOT plus 1/2 AT squared. We're solving for dy. The initial we had 7.6. The time here is 427 plus 1/2 negative 9.8, 0.427, and then don't forget to square this. That's a big error I see students make. And then we just calculate that out. So I get 2.35 meters. Just remember, this is the height above the ground, but the goal itself was 2.44. So that means we're below the crossbar, right? So that means we score. Goal. And we are exactly, what is that, 0.09, not exactly, but approximately. There's going to be some rounding error here, but I'm about 0.02 meters below the crossbar. And that'll be a goal. All right, moving on to the last problem. All right, we got the infamous monkey versus hunter problem. So just a reminder of the setup for this problem. We have a monkey hanging from a tree. We have a hunter who's taking straight aim at the monkey. Okay, the monkey's going to let go at the same exact time that the hunter shoots. And then conceptually, we know that the bullet and the monkey fall at the same rate. And therefore, even though the monkey lets go, the monkey's going to get hit. So we've talked about this problem conceptually. I'm sure you've seen demos of this, but now we're going to go ahead and prove mathematically why the monkey gets hit. So the first part of this problem, though, is we just want to figure out the angle that the hunter aims at. So this is just a simple trig problem. So go ahead and let's go and do it. So the monkey's 20 meters high, and the hunter is 10 meters away. Right? So it's a nice simple triangle, right? Here's 20, 10, oops, not to scale. 20, 10, let's find theta. So we'll use our tangent function. Tangent equals 20 over 10. And you get an angle of 63.4 degrees. Okay, all right, so let's get to the meat of the problem now. All right, so let's go through kind of the theory of what we're going to be doing now. We're essentially going to be trying to figure out where is the bullet? Where is the bullet when it reaches the monkey? Okay, if we can find that distance of where the bullet is when it reaches the monkey, that's one. And then the next thing we're going to do is find out, well, where is the monkey when the bullet reaches it? And those two heights should be one and the same. And that will essentially prove that the monkey gets hit. So the first thing we're going to do, let's go ahead and fix that velocity initial. So I'll go over and do this on the side here. So this is 14.9. So let's find the two components of velocity. This was 63.4 degrees. So we're going to go 14.9 cosine of 63.4. This side, we're going to go 14.9 sine of 63.4. All right, for the first one, the cosine, I get 6.67 meters per second. For the sine, I'm going to get 13.3 meters per second. So again, what that's telling me is the initial velocity in the x direction, 6.67. The initial velocity in the y direction is 13.3. All right, let's finish up everything else we know. So we know the acceleration in the x direction. There is no acceleration once the bullet's in the air, horizontally, that is. Now, vertically, there definitely is, right? The acceleration in that direction is going to be negative 9.8 as it goes up and then falls back down. Then the last thing that we know is the displacement in the x direction. So the monkey is 10 meters away. Now we do not know the displacement in the y direction, but that's what we're going to try to find. So as usual, time is kind of the component that's the same on both sides. So let's go ahead and find the time on the x side, and then we'll know the time on the y side. So on the x side, we'll use this, d equals VOT 1/2 AT squared. So 10 meters equals 6.67 times time, and then this goes to 0 because there is no horizontal acceleration. That gets me a time of 1.50 seconds. All right, so let's go ahead and now find the height. So where's the bullet? How high is the bullet at that point? So we'll just use that time. We'll use the same equation, but we will now find the vertical displacement. All right, so delta D, the initial is 13.3. So remember, we're using our y values here. We'll use that time that we just calculated, plus 1/2, negative 9.8. Then we'll go ahead and go 1.5. Don't forget to square that out. So that gets me a height, delta D, of, I guess that's 9 meters. Yep, 9 meters. So if we look back on our graph, that means the bullet is 9 meters above the ground when it reaches kind of the plane of the monkey here. The last thing we're going to then do is find out how far does Curious George, or the monkey, fall. So the time is the same, right? So we know, let's go ahead and do the givens for CG. So CG has an initial velocity of 0, and they're going to fall with an acceleration of negative 9.8, right? So the monkey's right there. They're going to fall down, and we're going to see how far does Curious fall in 1.5 seconds. All right, so we'll use the same thing, d equals VOT 1/2 AT squared. Now his initial velocity is 0, and we're going to go negative 9.8 and then 1.5 squared. So he falls 11 meters, right? That means this distance is 11 meters. That's how far he falls. So notice, since the total was 20 meters, Curious George is now going to be, at this point, 9 meters above the ground. So the bullet's 9 meters above the ground, Curious is 9 meters above the ground, and boom, he gets hit. All right, I hope that was helpful. If you have any questions, please let me know. If you'd like me to make more videos like this, please let me know. Otherwise, have a wonderful day.